Dr. Garcia, and I'm presenting Chapter 12, Understanding Research Results, Description, and Correlations. For week 13 for Psych 3040 research methods. Now remember, as always, that this video is only a supplement to your readings, and your readings will provide you with a little bit more depth than what I can do within this video slides. And also know that chapter 12 is a bit of a review. So scales of measurement review, we're going to do a review on scatter plots and correlations, which are things that we talked about very early on in the semester as well. So let's do a review of the different types of scales of measurement. Now, first of all, some of your data that you're going to be collecting and that you have collected is called nominal data or categorical data. These data represents that the levels that exist within the data that you've collected represent different categories or groups. This is non-numerical data. You might have a number to identify it, but the number represents a level. So for instance, if you think about it, so are you a low social media user or a high social media user? You can be assigned a code of 1 as a low social media user or assigned a code of 2 as a high social media user. And those are categorical groups. You're either a low user or a high user. You're not in both of those categories. So even though you're given a number, that code only identifies you by the group that you belong to, but it has no numerical value whatsoever. So you will have data that is nominal or categorical. I always like to kind of make sure that I reference categorical because it helps to remind you to know that what category that you belong to. So for instance, if you're asking questions about ethnicity, what category of ethnic identity do you prefer? Do you exist in the category of, Caucasian, African American? You could be mixed of some of these things. Either way, you're categorical. Ordinal data is rank levels from low to high. So letter grades are ordinal data, results of the Miss America contest as nominal data, and anything that's on a Likert scale is considered ordinal data as well. So ranking systems from low to high. So like, how do you feel today, from very unhappy to very happy? This is also considered ordinal data. Then we have interval data. The interval data is when you have, first of all, no absolute zero, can be summarized using means or arithmetic averages, and an interval data is very much like IQ scores because there's intervals between levels that are equal in size. So there's an interval between 85 to 100, and that's equal in size to an interval between 100 and 115 based on IQ scores ranging from 55 to above that as well. So this is considered interval data. Now, ratio data is when the data does have equal intervals. There is an absolute zero. And here we're looking at things like height to weight ratios. So anytime when you're using a ratio, it is like a height to weight, it is considered ratio data. For our purposes, we typically will use in your studies nominal data because you have categories that people belong to. Maybe you're looking at the difference between whether or not people protested or did not protest. They went to the protest for social justice or non-protesters. And so that's categorical data. That's another example. And then your ordinal data is your data that you're collecting on your dependent variable measures when you're asking people questions about, rate how much stress you have felt recently, or tick off all the things that have made you feel uncomfortable when you listen to this TED Talk, right? And so you get a number or a rank or from low to high of how many things people are ticking off. So that's ordinal data. These are the two that you're typically going to be working with. Now, moving right along, there is a Likert scale dilemma. Technically, Likert scales, as I said before, are ordinal data because they have response categories in a Likert scale and there is some type of rank order, and it typically goes from low to high. However, it is also common practice to assume that Likert scales are also interval scales. If a researcher takes it as an ordinal scale in the absence of the mean and parametric tests like t-tests, ANOVAs, etc., they cannot be performed. Basically, what this is telling us is that SPSS does not recognize Likert scales as ordinal because technically Likert scales, although we identify them as ordinal scales, they could also fall into the category of interval scales if you really wanted to, based on a statistical theory. So SPSS, therefore, will not recognize Likert scales as ordinal, and therefore you must assign these as scale in SPSS. So when you look at the column measure, when you're in variable view, you're going to see nominal, ordinal and scale data. And you're going to, even though again, your Likert scale technically is considered ordinal data, you're going to have to define it as scale in SPSS because according to specific statistical theories, Likert scales are identified in ordinal, but also can qualify as interval. And SPSS knows that and therefore doesn't like our data to be measured as ordinal, and therefore we change it to scale. When you describe results, there's a lot of ways of doing that. You can compare group percentages, you can do looks at correlations on scores, or you can even compare group means. So we're going to take some time to look at the different ways that we can present this data. So first of all, again, describing results is part of our descriptive statistics that you're working on in lab activity number 9. One way that you can look at your descriptives is doing a frequency distribution. A frequency distribution is the number of participants who receive each possible score on a variable. So let's say you had asked people to fill out a score. There was 10 scores on a range of 1 to 5, and 2 people answered 1. 5 people got a 2. 4 people got a 3. 2 people, the frequency of that, we see 2 of them here as well, got a 4, 2 here. And then only 1 person scored a 5, and we see that single one here. So these are a range of scores from 10 different people on their scores from 1 to 5. And again, we see for 1s we got 2, then we have 5. For 3 we have 4 people. For the 4s only 2 people, and number 5 for 1. So these are frequency distributions. And this is very much just a review from your stats classes that you would have taken. So you can graph frequency distributions in pie charts, bar graphs, frequency polygons, or histograms. In your lab activity, it will ask you to go ahead and do a bar chart or a pie chart of a frequency distribution. It's up to your choice to decide which variable you want to use, but I know the lab activity does ask you to run a frequency distribution and then present it in a form of a chart or a graph. So here's a couple of examples of a frequency distribution. Here's one with a bar chart. This is the superhero battle winner when they looked at different movies, and Batman won 52, Captain America 25, Iron Man 34, and Superman only 17. So this is the frequency of times that this superheroes won certain battles. We can also look at frequency distributions in a form of a pie chart, those people who like to travel versus those who do not. 70% versus 30. So this is just a percentage valued versus a raw data value. Again, the number of times each one of these superheroes won a battle. Batman won 52, Captain America 25, 34, and 17, and so forth. So this is what we're looking at when we're looking at frequency distributions. This is the bar graph that displays the data on those who like travel preference, like or dislike. And again, you have it on the frequency of 70 and 30 on that percentage point. What we're going to look at now is hypothetical data on a hypothetical experiment looking at scores on an aggression measure, again, in a hypothetical experience. So then you had a group that had modeled aggression behavior and a group that had no modeling of aggressive behavior. And you can see the sum here of F52, the sum here of 31. You can see the means, the variance, the standard deviation, and the n, the total number of people is n. Again, your variance and standard deviation here. Again, this is just a review of basic descriptive data that you would have learned how to understand and to have run some stats on in your 30/20 class. But just to kind of get you to see that there were 2 different groups. Some were modeled aggression and some groups had no modeling of aggression in their condition. And as you can see here, scores on the aggression measure, the people who had no modeling of aggression, their scores on aggression behavior, pretty much some people went up, peaked at 3, and then went down. But the group that had aggression modeled for them, their scores didn't start out as 0. They actually started at 2, peak up a lot higher than the no model group, and then go down from them. So you can even do an overlap. This is a frequency polygon. We look at the frequency of the aggression scores of group 1 and the frequency of the aggression scores of group 2. And this is a nice way to visually look at 2 different groups and sort of how they responded to this dependent variable measure of aggression. This is another way of a histogram showing the frequency of responses in the modeling aggression group. So the group that saw or witnessed aggressive behavior, so they were modeled aggressive behavior and what their scores were like. You can see that here 3 people got a 1, oh, excuse me, one person got a 3, one person got a 4, and then we have 4 people got a 5, 3 people got a 6. So we can see they peaked out here, and one person got a 7. So the average here is closer between 5 and 6, maybe 5.3, 5.4 or so. Okay. So those are just some ways of showing your frequencies and knowing reminding you what a frequency distribution is. The number of participants who receive a particular score on a variable. We kind of reviewed that there. And these are the different ways that you could graph that. Bar charts, pie charts, another example with a polygon graph, and another histogram of how you could do that. Now, when we go to descriptive statistics, we're really talking about describing the data that you have in the framework of central tendencies. The central tendency is the typical value for a distribution. And the different indicators of central tendency are mean, median, and mode. Again, just a review. The mean, you add up all the scores, you divide by the number of scores that you have. It's usually measured on interval or ratio scores. You will be able to compute means in SPSS. You've done that before in 3020, likely if you've taken it using SPSS, or in R, you've learned how to calculate means as well. The median is the middlemost score, the score that divides the group in half. And then the mode is the most frequent score, the score that is popping up most often in your distribution set. And so we have mean, median, and mode as measures of central tendency. You also can graph relationships when you're descriptive data in mean, median, and modes, so to speak. You can use bar graphs when you're graphing relationships. So here you can look at internalized behavior and externalizing behavior, externalizing behavior, and males and females. You can see that males score lower on internalizing behavior, things like low mood, feeling depressed, poor self-esteem. But they score much higher on externalizing behavior. Externalizing behaviors in psychology are things like having outbursts, getting into fights, property destruction, things of that nature, where you see these external or outward expressive natures of emotion. So you can see males have lower internalizing behavior, but males, but they have much higher externalizing behaviors. Now, females, on the other hand, have much higher internalizing behaviors at 63% compared to males. You can look at the differences here in internalizing behavior. Again, low mood, feeling depressed, poor self-esteem. We can see that females score higher more often on internalizing behaviors than males do. Same thing with externalizing behaviors. Males are demonstrating higher rates of externalizing behavior compared to females, less likely to engage in property destruction, assaults, and fights. You can also use line graphs as well, for instance, scores on a test. So you can take quiz 1 average scores, quiz 2 average scores, quiz 3 average scores, and so on. And this is a line graph to show the relationship of each quiz week by week. And we can see that people, but towards the end of the 5th quiz, they're doing pretty well. Descriptive statistics, again, going over this very quickly, just some terminology that you will need to know, because I am going to ask you, and APA requires you to report means and standard deviation and sometimes the variance of your data sets when you're writing up your results section. So just as a reminder, and understanding the type of descriptives that you're going to be pulling and what you're going to be seeing on your SPSS output tables, is that there's a notion of variability. Variability is the amount of spread in the distribution of scores. In other words, how far from normal or the average is the spread of your scores? What is the variability of your scores? Generally, you do want some variability in your data scores. You don't want everyone to have the same exact responses, because then you wouldn't find any differences. And that's what all of your hypotheses are looking for, right? They're looking for the differences in trust in law enforcement based on whether you protested or you didn't protest. You're looking at the differences in that trust level based on the differences in the experiences that you might have. So variability is important. The standard deviation is the amount of variation of data values in relation to the mean. So how far do your data points vary from the mean. If you have a low standard deviation, that means that all data values are pretty close to the mean. And again, that's a little concerning. You don't want a low standard deviation, because then that tells you that all the data that you've collected and all the scores that you have are so close to the mean that there is no variation or variability, and you will likely not find any differences. The variance is very simply the square of the standard deviation, S squared. Standard deviation is defined as S or SD. You'll report it in your results section as SD. Variance is S squared. The range is the difference between the highest and the low scores in your data set. So again, just some review and reminders of some of these descriptive statistics. And again, you will be seeing these in your output tables in SPSS, and you will be asked to report these not only in your lab activities, but more than likely you'll also have to report some of this in your results section and in your methods section of your final research papers. Now, correlation coefficients are important because you will be running correlations as well for lab activity number 9. It's always good to get a visual inspection of what's happening in your data before you run your inferential statistics if you can. So Pearson product moment correlation coefficient, or Pearson's R, describes how strongly variables are related. You can only use this data with interval or ratio scale data only, like a Likert scale data only. You cannot try to use correlations with nominal data. Like, you can't take gender and ethnicity and try to run correlations. It won't work. Gender and ethnicity is considered nominal or categorical data. So you cannot run correlations with nominal data. You only can run them with interval or ratio scale data, basically your Likert scale data. The correlation coefficient gives us the strength and the direction of the relationship. Again, this is a bit of a review because we did talk about relationships that variables could have in running these correlations earlier on in this semester. I want to say during week 2, I believe, is when we present the basics of understanding variables and how they could be related. You also would have done some correlations as a brief activity in most of our stats classes as well. So correlations tells us the strength of the relationship and the direction of the relationship. And the direction can be positive or negative, and we'll go over those right now. And the values can range from -1 to +1. And you will be asked in your lab activities as well to run some correlations and do a visual inspection of scatter plots and try to make sense and an understanding of the correlation between two variables that you would have selected, that you and your group mates would have selected. So let's take a look at that. You would have get scatter. We're going to ask you to run scatter plots on these correlations. And so you'll run a correlation, you get scatter plots. And again, it's a range from +1 to -1. Anything that's a positive means that's a positive relationship. Now, this is a fictitious data plot. This is a perfect relationship. What this tells us is that as variable X increases, so does variable Y. They are both moving up in the same direction. Now, this particular, when you have a negative relationship or anything that's a -1, now remember, when you're doing correlations, they range from -1 to +1, with 0 in between the -1 and the +1, right? So the closer you are to 0, then that means you have no relationship. 0 relationship is going on. But if you are on the negative end, then that means as one variable goes up, the other variable tends to go down. So negative relationship doesn't mean that both are moving down in negative direction. It just means that as one goes up, the other goes down. Let me give you an example of both of these. And I've used this example before, I believe, earlier on in one of our videos, so we'll be consistent with this. You can think of this in terms of attendance rates and test scores. If you continue to attend class, you have high attendance rates, then there's a positive correlation with high attendance rates and high test scores. And we can take that same idea and look at it in the framework of absenteeism and test scores. That's the first one I said was a positive relationship. As one goes up, as your attendance rates continue to go up, so do your test scores. They both increase at the same time, and this is considered a positive relationship. Now, a negative relationship is when one goes up and the other goes down. As one variable goes up, as we see here on the variable Y, the other variable goes down. And so an example of that, going back to that same example, is absenteeism and test scores. As your absenteeism goes up in school, we know this happens with not only elementary, middle school, high school, but also for college students as well. It doesn't matter what age or grade of college school that you're in. If your absenteeism goes up, then guess what tends to happen? You will have lower test scores, and overall grades. And that's considered a negative relationship. As one variable goes up, if your absenteeism goes up, then that's what's going to go down. Your test scores will go down. So again, just a review of what these are. These are some scatter plots that depict the patterns of correlations. And again, this is what you saw here is a perfect positive, perfect negative correlation. But this is more likely what you're going to see. You're going to see these points are really reflected of the data points or the observations of each one of those scores. In this case, there's 10 scores here. So there was 10 people or participants in this particular study. And these are their scores. And you can see there's a positive relationship. And it says it's a plus 0.65. 0.65 is a pretty strong relationship. It's pretty good. That's a pretty decent number. Again, that positive relationship is as one goes up, the other variable also increases at the same time. So there's a positive relationship between these variables at 0.65. You can look at this particular scatter plot here, and we can see that it's identified as a negative 0.77. And again, it's closer to that negative 1. It's not close to 0 at all. We're concerned about 0 because there's no relationship. But here we have a negative 0.77. This is a very strong negative relationship. And we can see as one variable goes up, the other variable continues to go down. So that negative relationship can be seen here. You're always going to see positive relationships between two variables moving up in this upward direction, and you're always going to see negative relationships between two variables moving downward in this left to right direction. Whoops, let me go back here. And then again, just to show you here, this is no relationship whatsoever, right? So we have a 0.0 relationship. There is no pattern moving up in this direction or moving down from left to right. We could see that the observed scores or the data is scattered with no specific direction. And we can see by this number 0.00, that means that there's zero relationship or no relationship whatsoever. You can also do correlations with a full range of scores, a restricted range. You can see here if there's a full range of scores, you're like, oh, this is interesting. It doesn't look like much is going on, but wow, look at this. There seems to be a pattern of a positive correlation when we look at the entire range of scores. However, if we were to do a restricted range, because when we look at this, we could say, wow, we could really see things happening and picking up right here. I wonder what's going on in this full data set. Let's block these guys out here because we can see that there's a distinctive, strong, positive relationship in this upward direction. But let's go ahead and sort of like blank these guys out for a moment. And let's just look at this restricted range of values. And you can see here within this restricted range of values between 0 and just over 5, we see that there is no correlation or no relationship between these two variables. But when you add in data points that are maybe 5.5, 5.75 and above, you absolutely see this positive correlation as well. So this is important to look at when you're visually inspecting your data. You do want to go ahead and look for that relationship. Is it moving upward? Is it moving downward? Is it positive? Is it negative? But you also want to pay attention to the nuances within the scatter plot as well. As you can see here, let me look at this one, it's easier. There's really no relationship here. But you can see with these ranges of scores up here, there's a strong positive relationship. When you look at it all together, it appears as there's a positive relationship with a few points going on. But when you really look at them within these restricted ranges, there doesn't seem to be any pattern whatsoever. It's fairly like a non-relationship. So it's important to inspect your scatter plots to look for where and how these relationships might occur. And we will help you through this as well when we're working with you. Curvilinear relationship, scatter plot of a curvilinear relationship. We discussed this a couple of weeks ago, and this came up in our Q&A session as well for one of the classes, and people asked to review the curvilinear relationship, and that was good. I think both classes asked for a review of that. And again, this is when you have one independent variable and you have 3 different levels of that one independent variable, and you're trying to understand the relationship. So remember, if you recall on that particular example from a couple of weeks ago, there was time of day, morning. They wanted to see what were the energy levels of college students. So I'm just kind of bringing that as the example for this curvilinear relationship. You have one independent variable, and that independent variable is time of day. And the researchers wanted to know at what time of day do college students have the highest energy level. So at time 1, or in the morning session, college students seem to have low energy levels. But at time 2, in the middle of the day, college students had high energy levels. But at time 3, in the evening, at the end of the day, after they've gone home and had a long day, they again have low energy levels. So a scatter plot of a curvilinear relationship is really looking at a single variable and that has different levels and trying to see how this relationship works. Again, you can have an inverted U shape like this, or you could have had something like a actual U shape or V shape that looks something more like this as well. But this is an inverted U shape from time 1, time 2, and time 3. Low energy, high energy, low energy. Morning, midday, evening. Okay, so just a review of that. Now the effect size is very important. You will need to calculate your effect sizes as well. You'll need to report your effect sizes when you run your correlations and when you run your inferential statistics. If you recall in your stats courses, you would have run your inferential statistics and your correlations, and you could get a good, solid statistical significance in your inferential statistics. Maybe in a t-test or in ANOVA, you got statistical significance. But that statistical significance isn't as meaningful if you have a low effect size, because the effect size tells us how strong is that association or relationship. So here, the effect size for correlations is the strength of the association between the variables. Pearson R is an indicator of the effect size, and it tells you how strong it is. This also tells you the effect size here. It has a small effect if it's 0.15, a medium effect, 0.30, but it's a large effect if it's above R as well. The larger the effect size, then the stronger the relationship. So even though you can identify, like here, we can see a positive 0.65 relationship, negative 0.77 relationship. These seem like very strong relationships, and we can say that it's a strong positive relationship or it's a strong negative relationship. But moving on, you need to be able to calculate your effect size as well. The good news is you won't have to hand calculate effect sizes, because when you run a scatter plot in SPSS, it'll provide you with the effect size in the upper right-hand corner of that scatter plot. That's important to know, because you need to know where to find it. You will find the effect size of the correlation in the scatter plot that you produce in SPSS, and it's located in the upper right-hand corner of that scatter plot. So you don't have to do any hand calculations, but you do need to report them, and you will want to refer to your textbook or to this slide to recognize what is considered a small, a medium, or a large effect size for your correlations when you run them. Now, when you run your inferential statistics, you're going to see this next time in our next slides in our future chapter 13, you're going to have to request SPSS to provide you with the effect size. So there are certain places that you will need to click in SPSS to get that in your inferential statistics. We will review that in upcoming weeks, but for now, just do know and understand that your effect size is important to report when you're running a correlation. You don't have to do hand calculations. Once you request a scatter plot for a correlation, SPSS will show you the effect size in the upper right-hand corner, and it's identified as an R. It looks like this. R equals, and it'll have the number there. You just need to refer back to your text or to this slide to know what is the actual effect size. Is it large? Is it small? Is it medium? Okay. Partial correlations are also important that you can do. We won't be running any of those in this particular class. We usually do partial correlations when we have our advanced statistic classes for undergraduates and some advanced statistic classes in our graduate program. But just know that partial correlations can be run if there's a third variable problem. As we talked about before, we always want our studies to have making sure we have high internal validity, and in that our independent variable or one variable in fact has a specific relationship to a second variable, that those are the two things that are operating. But sometimes there could be that third extraneous variable or confounding variable that you can't control and may be responsible for the relationship between variables 1 and variable 2. So you can run partial correlations to statistically control for that third variable. So there's a third variable problem that can happen in many of our research studies. There are confounds. This is why, for some of you, for a couple of groups, You had to be very, very careful in how you designed your studies and how you put them together in Qualtrics, because there were lots of possible confounds or third and fourth and fifth variable problems that could have really tainted your results, and then your data would not have been very valuable whatsoever. So it's very important to try to make sure in the methodological process that you try to eliminate any third variable or confounding variable problems. You can deal with them later on with partial correlations, and you can deal with them in ANOVAs as well using a covariate, but that's a little bit more sophisticated statistics that you would learn in our advanced classes. But in general, the goal as a researcher anyways is to make sure that you're really thinking about your design, your measure, your variables, the methods, how you're producing your studies, and how you're going to execute it to minimize any third variable problem or some uncontrolled extraneous confounding variable. You don't want some other outside variable to influence the relationship or the direction of the strength of the relationship between your existing variables 1 and 2. Moderating variables is another thing we can look at in regression, that if there is a third variable impact, like there is a third variable problem and we had no way of controlling it, you can actually run a statistic called a regression, and you can put in moderating variables to look at how that third variable maybe strengthens or weakens the relationship between variable 1 and 2. I have only done this with our undergraduate research courses maybe about 2 or 3 times for our students. I love moderation and using moderating statistics and looking at variables, these third and fourth confounding variables, because they're very difficult to eliminate in a lot of research studies. But I've actually very rarely have had students had to do this, but don't be surprised if I realize, you have all this great data, but I really think that there's a third variable operating that was not accounted for. And so I may ask you to run a regression using moderation, and I will show you and train you and help you run that if needed. Just to show you here, we won't do this. Again, this is definitely for not even graduate school, but usually for doctoral programs, but just so you know, this is sort of where we headed in looking at more sophisticated correlations. There's other correlations called regressions. I don't have them in here. They are in your textbook, but I'm not presenting them here. We don't really do regressions in this class. Some groups have, and I teach them how to do that if they needed to. But just so that you know, structured equation modeling, or SEM, or hierarchical linear modeling, is a very important statistical strategy to use. It describes the patterns of relationships amongst quantitative non-experimental variables. So as you can see here, it picks up these correlation scores, but it gives you how does attitude and subjective norm and behavior all play a role into consume alcohol. And when you add all these together, what is that relationship between intention to consume and the actual behavior? So it's like you bring in multiple variables and you're looking at these pathways or theoretical path diagrams that help us to understand these relationships with more than 2 variables. Here you're looking at 5 different variables. So it's the statistics are coefficients, just like we see the Pearsons are. Pretty similar to regression equations, which I didn't really present here, but indicates the strength of the relationship between these variables and how they are all operating together. Just something to kind of keep in mind, nothing that you will have to do in this class. And that ends our presentation. Thank you.